dinde is an experimental statistical analysis system written entirely in Lisp. It runs on the Xerox family of personal Lisp workstations and depends on the Lisp object-oriented programming system called loops. In dinde, we take advantage of this environment and the high-resolution bitmap display to develop a visual representation of a statistical data analysis. In the bottom left corner of the display, there is a window entitled Demographic Analysis. This window is a view of different objects of statistical interest, and the view itself is called an analysis map. The objects in this view are three: a string vector containing the names of 49 different countries, a float vector containing the number of infant deaths per 1,000 live births for each of the 49 countries, and another float vector containing the per capita gross national product for each of the 49 countries. These are independent objects in dinde, and as such may be interacted with through the analysis map using the mouse. In particular, we can give each of them a name, or we can add notes to them as we learn more about each object. As you can see, when I hold onto a particular menu item for any length of time, some text is displayed in the window above the analysis map describing the result of selecting that menu item. Pervasive throughout dinde is the ability to zoom in on the details of every statistical object. Zooming in on the country string vector, for example, produces a number of windows which display the internal details of that string vector. As we can see, its elements are the names of each country, and they are arranged in alphabetical order. To remove this detail from our display, we need only close the window. Similarly, this window, the analysis map itself, is a view on these three statistical objects. As such, it has behaviors which allow us to narrow the view, perhaps removing some of the objects that are already in the display, or widen the view, adding new objects to the display. Most often in dinde, we add a new object by selecting the Add a New Kind of Analysis node. Selecting this, we're prompted for the name of the class of that node. All such classes are contained in a window called the dinde toolbox. Opening the toolbox, we see all of the possible classes that are available in dinde. These are arranged in order of increasing specialization from left to right. In particular, then, we have a general kind of array and three special cases for that array, namely matrix, scalar, and vector. Then in turn, for each of these, we have either matrices with Boolean elements, float elements, or string elements, and so on. We also have a whole host of graphics available in dinde. These are divided into one-dimensional plots and two-dimensional or XY plots. Again, you see that the one-dimensional plots are either box plots or histograms, and two-dimensional plots are QQ plots and scatter plots and dynamic scatter plots. And these are, again, further specialized. A different kind of class is something we call a statistical situation. These represent less familiar artifacts of a data analysis, such as fits, or decision nodes in the analysis, such as a bivariate regression. For this particular data set, I'm interested in regressing the infant death on the per capita GNP, so I select a bivariate regression from the toolbox, and I'll close the toolbox. dinde constructs the bivariate regression and then prompts us in this black prompt window for the values that a bivariate regression needs. In particular, it needs an X variable, an explanatory variable, which I'll select to be the per capita GNP, and a Y variable, which I've decided will be infant death. I'm also given the option of attaching labels to each of the points in the bivariate regression, and I'll select the country. Back in the analysis map, I'm now given the opportunity to link this new node in the analysis to existing nodes in the display. To demonstrate the logical flow of the analysis from the two data vectors to the bivariate regression, I'll choose to link the bivariate regression to each of them. In this way, we see that the flow of the logic is from the two data vectors to the bivariate regression. In dinde, we represent a statistical data analysis as a collection of directed acyclic networks, where the nodes of each network represent artifacts of the analysis or decision points of the analysis, places where we may entertain taking new actions. As such, I have the ability to rearrange the nodes of the network in a way that make the most sense to me for the logic of the analysis. Thus, the analyst is given the power to actually break links and make links between objects in the network. The analyst is also allowed to insert objects called memos between two nodes. These objects will just be repositories of information on the logical flow of the analysis. They'll just have notes added to them. Another way in which the analysis can grow is by examining each individual node and seeing what specific actions can be taken from that decision point. Here for the bivariate regression, we see that we can inspect the data in a variety of ways: scatter plots, histograms, or box plots. We can fit a straight line to the data, either using the resistant line fitting technique or the least squares fit. If we're not certain what to do at this point, there are also some suggestions made available. When selected, the suggestions produce canned text which describe, given the context that we're interested in doing a simple bivariate regression, what one might do first. In this case, it says that generally one should inspect the data visually. In particular, look at a scatter plot. Let's return to the analysis map then and do exactly that. So selecting the methods available for a bivariate regression, we look at the inspect data and choose scatter plot. Selecting scatter plot causes dinde to produce a new object called a dynamic scatter plot and to prompt us for a position on the display to show the plot. Here we see the infant deaths versus the per capita GNP for each of the 49 countries. We can identify countries simply by pointing and selecting them with the mouse. This inverts the displayed cross and shows the label associated with that point in the display. If we like, we could label the point on the display itself. Just like bivariate regression, scatter plots have specific methods associated with them. In particular, we could add a straight line of some sort, or smooth the y's, or save the display data, or look at some suggestions if we're not certain what to do. Because of the curvilinear relationship present in the plot, I'm going to look at a smooth of this plot. In particular, I'm going to look at a running linear smooth of the y's. Then calculates the smooth and adds it to the plot. As was the case with the individual points, the smooth can be selected and it displays the information that it's a 10% span, and it can be labeled. An alternative to fitting a smooth curve to this data, we could try and straighten the plot itself by choosing a re-expression on the plot menu. This prompts us with a new set of menus displaying the Tukey's ladder of power transformations for both x and y. I'm going to select the natural logarithm of both the infant death and the GNP and plot the transformed data. As can be seen, this plot is definitely more linear, one which we might be more willing to fit a straight line to. We can also see obvious outliers such as this point here, which corresponds to the country Taiwan. Another outlier that is somewhat more consistent with the data is India, as shown here. Because of these outliers, I'm going to fit a straight line to the data, but I'm going to choose a resistant fitting mechanism. This is described in the prompt window above here. So I'll select the resistant line fit, which DIND calculates and adds to the plot. As before, this line is selectable and presents its information associated with that line in the window above the plot. Let's close that plot now and examine the state of our analysis according to our analysis map. Here we see that the network itself has grown. That as a result of an action taken at the bivariate regression step in the analysis, a scatter plot was produced. Similarly, as a result of actions taken at the scatter plot, a bivariate fit was produced representing the fit due to the running linear smooth, and a bivariate resistant fit corresponding to the resistant line. Like all objects in the analysis map, these nodes can be zoomed in on. Zooming in on a plot, for example, reproduces the plot. Whereas zooming in on an artifact like a fit produces the internal information that is relevant for that kind of node. Here for the resistant fit, we have a microscopic view of its internals. We see there's some diagnostic information, such as ratio of the half slopes, slope of the right and left halves, number of iterations, and so on. Like the analysis map itself, this microscopic view is mouse sensitive. So clicking on the residuals here, I could give the residuals a name, or add notes to the residuals, or zoom in on them, just as I could if they were appearing in the analysis map. Let's close the microscopic view in the plot. Again, this is a new decision node. The bivariate resistant fit is a new decision node in our analysis. As such, there are a number of actions that one typically wants to take. In particular, given any fit, one wants to do a variety of residual plots. So I can plot the residuals versus x, their index, the fit, a histogram, or a QQ plot of the residuals. I'm going to look at the plot of the residuals versus the fitted values. Here again, we see that we can identify the points, and here's Taiwan, as we would have expected. And also, because of the context, again, that we're plotting residuals versus fitted values, there are some actions that are often appropriate to take. For example, we can check for the heteroscedasticity of the error by selecting this. This provides a simple visual cue for our eye to determine roughly whether or not there's any heteroscedasticity present, and it looks like there isn't. Alternatively, I could have also ran a smooth through the residuals, a simple or running linear smooth, or added a straight line of some sort. Let's close this plot now. Again, the analysis map has been updated to reflect the result of the action we took at the bivariate resistant fit, namely a new residual versus fit plot. If we were to continue the analysis in this way, the display itself would soon become very complex. To alleviate the complexity, we can also hide some of the details from the present view. This is done by narrowing the view, again, in this case, creating a new view within the present one. Selecting Create a View causes a small icon representing an analysis map to appear in the top left corner here. And if we were to zoom in on this, we find an empty analysis map, as there are no members in the view of that analysis map as yet. In the window above the larger analysis map, we are prompted to add new members to the new analysis map. We do this by selecting appropriate members in the present analysis map. I'm going to add these two nodes to the smaller analysis, suppressing them from view of the current analysis map. Here's the bivariate resistant fit, and now the residual plot. In this way, we can have arbitrarily many levels of detail. For zooming in on this small icon in the analysis, representing a sub-analysis, I get the sub-analysis itself, from whence I could continue the analysis as before, with all of the results being reflected in the current view. Should I desire to have that detail back in the present analysis map, I can always choose to explode this nested analysis map. As so. And the detail is back. And of course, the inverse operation is available. Return the exploded map. And I can select the one. And the present view reconstructs itself, adding the new analysis map icon to the network. So the logical flow is maintained, and some of the details are suppressed. Let's consider what this analysis would look like if we were to do a more complete version of it. In all of its detail, the analysis as I constructed for this data yesterday is shown in this particular view. As you can see, that this soon becomes very complicated, but it still shows the logical flow from the data vectors, infant death, and the GNP. I have a bivariate regression step, then a dynamic scatter plot, and here's a resistant fit, and a number of residual plots. A more interesting view of the exact same analysis, reflecting a better organization of the analysis, is the following. Here, many of the details are suppressed from the view. But at the topmost level of the analysis, we can see that we began with the data, and here we went from the infant death to a marginal analysis of the infant death, from the per capita GNP to a marginal analysis of the per capita GNP, and from both to a regression analysis. Should I be interested in more information on these, I can zoom in. And again, in the regression analysis, we see that there are further levels of detail suppressed. Again, there can be arbitrarily many such levels. A different way of finding out what information is available is by simply looking at notes which I stored yesterday when I constructed the analysis. So editing the notes of the marginal analysis, I can see the name of the analysis, who created it, the date it was created, the time, and how this analysis was created. And then, yesterday I provided some notes on this particular sub-analysis, namely that a box plot showed that the data were quite skewed, and that a transform of -1 over the square root of infant death produced the most symmetric looking box plot. If I like, I can go and look at that box plot itself. Simply again zooming in on this sub-analysis, and we see the box plot here, and zooming in on the box plot produces the box plot. And here I see how symmetric the transform of minus infant death to the -1 over the square root of infant death is. If I like, I could perhaps look at other re-expressions using, again, Tukey's ladder. Here, I'll look at the lawn. And as we'll see, it's not nearly as symmetric as the other transformation. Let's close these up now. Close up the large analysis and the smaller, more compact analysis. Now I'd like to illustrate different views, different kinds of views of the same statistical objects. In the bottom view here, we have an analysis map, one of the sub-analyses that appeared in the previous set of nested analysis maps. Here we see the logical flow of the analysis from bivariate least squares down to bivariate fit. And if we chose, we could make or break links between any of these nodes and rearrange them to best suit our feeling for what the logical flow of the analysis actually was, including insert a memo between two nodes, which we've already done. The top view, on the other hand, is a view of the same statistical objects exactly, but you'll notice that the network itself is quite different. In particular, this memo is unattached to any of the other objects, even though we'd inserted it in the analysis map. The reason for this is that this view is not an analysis map at all. Analysis maps view the logical relationship between, as determined by the user, between these steps in the analysis. This view, on the other hand, is something we call a causal map. The arcs that it follows are the actual causal links between steps in the analysis. So that because the residual scatter plot was formed as a direct result of a decision taken at bivariate least squares, a causal link was made between the two, from the least squares to the scatter plot. You'll notice that, like an analysis map, we can widen, narrow the view, and perform various nested view operations. Notably absent is the ability to make or break any links. We denied this power to the user, feeling that the causal links themselves are sacrosanct and might be used for purposes of auditing or verification of a particular analysis. In closing, then, I'd like to just look again at the toolbox and point out that the most difficult aspect of this enterprise is in fact a challenging research problem, and that is to identify the decision points in any particular kind of statistical analysis. As we've done here for the simple bivariate regression, we will also need to do when we extend the analysis to new kinds of statistical analysis. We anticipate that this will be a challenging and interesting statistical research topic, and it is our hope that others will join us in the pursuit of this research.